Most cardiac patients don't die in the hospital, they die on the way to it. For decades, the ambulance was just a fast car. 5G just changed that. The golden hour is the first 60 minutes after a cardiac event, stroke, or major trauma. What happens in that window determines survival, brain function, and long-term recovery. Traditionally, the hospital is where clinical care begins, but the ambulance ride is where it should. So let me show you exactly how a 5G connected ambulance works, not the marketing version, but the architecture version. There are 5 layers. First, the sensor layer that includes ECG, SpO2, blood pressure, video camera, all generating continuous data streams inside the vehicle. Second, the onboard gateway, which is a ruggedized 5G CPE that aggregates all sensor feeds and manages the radio connection. Third, the RAN, where the ambulance connects to the nearest G node B, and as it moves, it hands over between cells. Fourth, the 5G core network, where QoS policies and network slicing are enforced. Fifth, the hospital edge cloud, where data lands, gets processed, and reaches the clinical dashboard in near real time. India is where some of the most significant real-world deployments are happening. Apollo Hospitals, working with Bharti Airtel, and Cisco have deployed 5G connected ambulances that stream vitals and live video to the ER team before the patient arrives. Doctors see the ECG, prepare the cath lab, and give instructions to the paramedic, all while the ambulance is still on the road. In Gurugram, Artemis Hospital with Medulance uses AI-assisted diagnostics in the ambulance itself, where the system flags abnormalities in the data stream before a human clinician even reviews it. In Europe, the focus has been on the network layer, specifically making sure emergency traffic isn't competing with ordinary consumer traffic. The 5G Barcelona, Connected Ambulance Pilot, and Ireland's SLICENET project both use dedicated network slices for ambulance data. Think of it as a reserved lane on the motorway where only the ambulance's traffic goes there, with guaranteed bandwidth, bounded latency, and protected QoS. No matter how congested the cell is, the patient data gets through. So between India and Europe, you get a complete picture, and that is rich sensor-driven care on one side and guaranteed network priority on the other. But here's where most conversations about connected ambulances stop, and it's also where the most important question begins. What happens when the 5G signal drops? The ambulance is at 120 kilometers per hour. The patient is unstable. The handover fails between 2 cells. What does the 5G network do? What does the clinical system do? And who decided what the fallback should be? This is where resilience engineering enters the picture, and it's where 5G connected ambulances get genuinely interesting for anyone who works in networks. A serious deployment cannot assume perfect coverage. It needs at least 3 layers of protection. Layer 1 is multi-rate fallback. If 5G NR drops, the system falls back to LTE automatically, maintaining the data stream at reduced capacity. Layer 2 is application layer buffering. The clinical software buffers the last several seconds of vitals data, so a momentary gap doesn't create a clinical void. The paramedic screen doesn't go blank. Layer 3 is local edge processing. Critical algorithms run on device or on the ambulance gateway itself, not exclusively in the cloud, for which basic anomaly detection continues even without connectivity. Now let's talk about QoS, or quality of service, because this is where the telecom engineering actually lives. Inside the 5G core, every data flow from the ambulance gets tagged with a 5QI value, which is a 5G QoS identifier. Life critical video gets a low latency, high reliability 5QI. Telemetry gets a different 5QI optimized for small and frequent packets. The policy rules in the SMF and PCF enforce these priorities across the session. What this means in practice is that even when the cell is under load, the ambulance's clinical data stream is treated differently from everything else on that G node B. It's not magic, and rather a policy decision enforced at the network level. Someone has to configure it, test it, and maintain it. That's the operational reality most demos skip. This is why the connected ambulance matters beyond healthcare. If a network can support a moving emergency workload where failure is unacceptable, coverage is imperfect, and latency is non-negotiable, it tells you something real about what that network can support in ports, factories, utilities, and public safety. The ambulance is a proof point, not because it is flashy, but because the consequences of failure are irreversible. This is also a sharper way to understand the gap between 5G marketing and 5G value. While speed tests are easy to publish, human outcomes are harder to fake. A connected ambulance forces the conversation away from peak megabytes and toward what actually matters in a production environment, namely continuity, timing, prioritization, and operational trust. Now, what does 6G add to this picture? Three things. First is integrated sensing. 6G networks will have native sensing capabilities built into the radio layer, meaning the network itself could detect physiological signals like heart rate, movement, even respiration, without requiring the patient to be wired up. Second is sub-millisecond latency with deterministic guarantees. Current 5G targets sub 10 millisecond. 6G targets sub 1 millisecond with deterministic delivery, meaning the network can commit to latency bounds contractually, not just statistically. That matters enormously for any real-time clinical protocol. Third is non-terrestrial integration. 6G natively integrates satellite and HAPS links into the same network architecture. For an ambulance in a rural area, a tunnel, or a disaster zone where terrestrial 5G is unavailable, 6G provides continuity through the sky. These aren't concepts. The TrialsNet Beyond 5G Smart Ambulance pilot in Europe is already testing the transition path from 5G to beyond 5G in exactly this scenario. So the simplest takeaway is that 5G in emergency care is not about faster internet in an ambulance. It's about compressing the distance between the moment something goes wrong and the moment clinical intelligence reaches the patient. Architecture, redundancy, QoS, and 6G are all part of that compression. When a network does that reliably, it stops being a telecom story and starts becoming infrastructure. If this kind of structured breakdown is your thing, please subscribe. Every week I cover 5G and 6G beyond the headlines, where the architecture, the business case, and the real-world proof points finally meet. I'll see you in the next one.